In this video, we'll talk about general antiderivatives of functions and how you might go about finding them. So what is an antiderivative? Well, as the name sort of suggests, anti and derivative, we're going backwards or undoing this process of differentiation. So an antiderivative for a function f on some interval is another function capital F, so that if I differentiate this big F, I get my original little f back for all points in this interval. Or using Leibniz notation, the derivative of f is little f. So right away we know how we can check if we've found an antiderivative. The rest of this section will go into how to actually find them. We know really easily how we can check them. All you do is differentiate. And if you get the function you want back, then you've found an antiderivative for your function. Some examples. X cubed over 3 is an antiderivative for x squared. How do we know that? Well, if I differentiate x cubed over 3, I get 3x squared over 3, which is just x squared, which is what I wanted. So that is an antiderivative for the function x squared. Sine of x is an antiderivative for cosine of x. How do we know that? Well, if I differentiate sine of x, I get cosine of x, and so we're good. Sine of x plus 3, that's the x in parentheses here, is also an antiderivative for cosine of x. Why? Well, if I differentiate sine of x plus 3, this just becomes cosine of x, and the derivative of 3 is 0, so plus 0, which is just cosine of x. So what's an antiderivative for e to the x? Well, I know if I differentiate e to the x, I just get e to the x back at the end. That means e to the x is an antiderivative for e to the x. But what else is? Well, so is e to the x plus 1. So is e to the x plus 2. So is e to the x plus 100.4. Really, e to the x plus any constant I want is still antiderivative here. Why? Because if I differentiate a constant, it goes away and doesn't show up in the actual derivative, which is what I'm looking for here for this kind of problem. What we notice here is we can get more general than just finding one antiderivative for a function. So the general antiderivative for a function f is written as f of x plus c, where this big F is any single antiderivative for my function little f, and this c is an arbitrary unknown constant. This c could be any number we want. It would still satisfy the fact that the derivative of big F of x plus c is still just little f, because I know that the derivative of big F is little f, and derivative of c is 0. From a graphical point of view, this also makes sense, because if I have the graph of my function big F, and I just shift it up by some amount, or down by an amount, these functions all have the same derivative, because the derivative is the slope of the tangent line, and at any given point, the slopes here are all the same because I've just taken the function shifted up or down. That won't change the slope of the tangent line at the point. It's also a consequence of the mean value theorem that this gives me all possible antiderivatives for the function little f, because we know if two functions have the same derivative, their difference must be a constant. And so, since all my antiderivatives must have the same derivative as a base one, they can only differ from it by a constant, which is this arbitrary c that we have in our definition. So an example, find the general antiderivative for f of x equals sine of x. Well, what do I differentiate to get to sine of x? Well, if I differentiate minus cosine of x, this gives me minus times minus sine of x, which is just sine of x. So minus cosine of x is an antiderivative. And what's the general antiderivative? Well, it's going to be minus cosine of x plus c. That's the idea of a general antiderivative and how you might go about finding it for a given simple function.